Scalar products and projections of vectors in 3D. So we've already seen the scalar dot product in 2 dimensions, and we've seen that the scalar dot product just ends up being the x components multiplied together plus the y components multiplied together. So this was for 2 dimensions. Let's have a look in 3 dimensions. When we take 2 vectors and take their dot product, we're looking at taking a vector. Let's look at its x components, x1i plus y1j plus z1k, and multiplying it by another vector with different x components. All the same, it doesn't matter. x2i plus y2j plus z2k. Taking the dot product just means expanding all these terms out. So we get x1, x2, I dot I plus x1, y2, I dot j plus, so that was taking the first term multiplying by the first two, so let's multiply the first one by the last one. So x1, z2, I dot k. Now let's take the second term and multiply it by all three. So we got y1, x2, j dot I plus y1, y2, j dot j plus y1, z2, j dot k. Taking the last term, multiplying by all three, we get z1, x2, k dot I plus z1, y2, k dot j plus z1, z2, k dot k. Now, a lot of these dot products, we know that when we have vectors that are at 90-degree angles to each other, so we can imagine I, j, and k, we know that I and j are perpendicular, I and k are perpendicular, and k and j are perpendicular. And when we have a dot product of 2 vectors that are perpendicular, we know the dot product is 0. So dot product of I and j is 0, I and k is 0, j and I is 0, j and k is 0, k and I is 0, and k and j is 0. We also know if we have the dot product of 2 vectors that are the same, for example, I and I, that's the same thing as the magnitude of that vector squared. And since these are unit vectors, the magnitude of a unit vector is 1, and 1 squared is just 1. So what we end up getting is I dot I ends up being 1, so we're just left with x1, x2 plus over here, j dot j is just going to leave us with y1, y2, and same with k dot k. It's just going to leave us with z1, z2. So we can see the dot product in 3 dimensions is very similar to 2 dimensions. It just adds in the extra z1, z2 term. So we can also use the dot product to reference an angle between 2 vectors, and we know that's equal to the magnitude of the first vector times the magnitude of the second vector times cos of the angle between those vectors. And the only difference here is that when we're finding dot products, we have the extra term here, and when we're finding magnitudes, we've got the extra term like in Pythagoras in 3 dimensions. So if you wanted, you could rearrange and make cos theta the subject, where we'd end up with a dot b over the magnitude of a times the magnitude of b. We know the dot product is equal to x1, x2 plus y1, y2 plus z1, z2, all over the magnitude of a which is going to be x1 squared plus y1 squared plus z1 squared, all multiplied by the magnitude of b, which will be x2 squared plus y2 squared plus z2 squared. And we can use these in 3 dimensions now as the scalar dot product. So let's do an example. Let's find the angle between u being minus 2i minus j minus k and v being I plus 2j minus k. So after the angle between them, we know that cos theta is just going to be the dot product of u and v over the magnitude of u multiplied by the magnitude of v. The dot product is going to be all the appropriate components multiplied together. So we're going to get minus 2 times 1 plus minus 1 times 2 plus minus 1 times minus 1 all over root minus 2 squared plus minus 1 squared plus minus 1 squared multiplied by 1 squared plus 2 squared plus minus 1 squared. And simplifying this is going to give us minus 3 over root 6 times root 6, which is going to be minus 3 over 6, which is minus a half. But that's what cos theta equals. So now we know that cos is negative. So that must imply that the angle is above 90 degrees. You can think about your all stations to central where cos is negative over here and here. But when we take a dot product, we're always assuming the angle is between 0 and 180. So we can disregard that third quadrant as an answer. So we know our answer is in the second quadrant. So we can get our angle, or we can get our base angle to use by let's just consider x equals the inverse cos of a half, which is going to be 60 degrees. And that would be the angle in the first quadrant. But since we're interested in the angle in the second quadrant, it's just going to be 180 minus 60 degrees, which is going to give us 120 degrees for the angle between those vectors. So let's have a look at projecting 3D vectors as well. So we're going to have a look at a vector A and a vector B, and look at projecting vector A onto vector B to give this vector here, and knowing an angle between those vectors. So we've already seen projecting vectors that this would give us, the projected vector here would give us, let's call it P. And this projected vector would give us A dot B over the magnitude of B squared times the vector B. And again, the only difference in 3 dimensions here is that when we take the dot product, we've got the extra Z term. When we're taking magnitudes, we've got an extra term here as well. So if you like to, you could think about the vector P being the dot product, which is x1, x2 plus y1, y2 plus z1, z2 over the magnitude of b squared, which is actually just going to be x2 squared plus y2 squared plus z2 squared. And all of that is going to be a constant multiplied by the vector B. And this is what happens when you're projecting A onto B. So it's always nice to imagine your formula as that term there as the one you're projecting. Let's have a look at an example in projecting vectors. So we're going to look at two vectors. Let's go A being 3i plus 2j minus k, and B being minus I plus 2j plus 3k. We're going to look at projecting A onto B and also B onto A. So remember, to get the vector, the projected vector, it's going to be A dot B over the magnitude of B squared times the vector B, when this is your projected vector. So this is going to help us for part 1. Part 2, our projected vector, we'll call it Q this time, that will equal B dot A over the magnitude of A squared times A, because in this case we're projecting vector B. So to do this, we need to do a few calculations. So let's find A dot B. That'll actually be the same for both because it doesn't matter the order for scalar multiplication. So let's find A dot B. So it's just going to be 3 times minus 1 plus 2 times 2 plus minus 1 times 3. So we're going to get minus 3 plus 4 minus 3, which is going to give us minus 2 for the dot product. Let's go ahead and find the magnitude of A squared, which is just going to be 3 squared plus 2 squared plus minus 1 squared, which will give us 9 plus 4 plus 1, which is 14. And let's go ahead and find the magnitude of B squared, which is just going to give us minus 1 squared plus 2 squared plus 3 squared, which is also going to be 14. 1 plus 4 plus 9 will give us 14. So to find P for part 1, we know it's going to be the dot product, which is minus 2 over the magnitude of B squared, which is 14, times vector B, which is going to be minus I plus 2j plus 3k. So we're just going to expand this out and simplify the fraction. We're going to get 1/7 I plus 2/7 j. So that should be a minus. Minus 3/7 k. So let's do the same for vector Q. So this is when we're projecting B onto A. So again, it's just going to be the dot product, which is minus 2 over the magnitude of A squared, which we know is 14, multiplied by the vector A this time, which is 3i plus 2j minus k. So we're just going to get minus 3/7 I minus 2/7 j plus 1/7 k.